Well, hello, all you beautiful people. What we are going to do right now is I am going to go over some more examples from the chain rule. We started this the other day, and so just to remind you, you're going to use the chain rule when you have composition of functions, so like an inside function and an outside function. So the rule is there's two different types of notation. If you have a function y that is a composition of f of g of x, that means g of x is a function inserted into f of x, you find the derivative by finding the derivative of the outside and multiply it by the derivative of the inside. So this is one way to write that. This is another way to write it. So if f is the outer function, you take the derivative of f. This is the important piece. You have to leave the inside alone, then multiply by the derivative of the inside. So let's do some examples here. So I want you to think about, so if we want to use this notation, you're going to be thinking about like what is the, here we're going to look at what the inside function is, and that's what you're going to let u equal. So this is a little bit different method than what I did the other day, so you guys are going to have to pick which method makes the most sense to you and stick with, I would suggest that you stick with that method. But I do want to show you this notation because it will come back in 2.6. We're going to want to use this type of notation in 2.5, and you'll see it, and you just need to know, okay, when you see a function y and it is in terms of x, so it's a y is explicitly defined in terms of x. When you're finding the derivative of y, you say the derivative of y with respect to the variable x. That's what that means right there that I just wrote in green. And what you're going to need to do to use the notation that's that you're looking at is we're going to want to let u equal the inside function. So look at your equation here, 3x plus 5, all of that is being raised to the second power. So the inside, our u, is going to be 3x plus 5. And so if we follow the notation that's up here, dy du, then what this means is if we let u equal 3x plus 5, then I can rewrite this as y equals u squared, taking that and replacing 3x plus 5 with u. And then what this means right here is dy du means find the derivative. If I'm going to find dy du, I'm going to, it's taking the derivative of u squared with respect to u, which would just be using the power rule. So bring the 2 down in front, u to the 2 minus 1 would be to the first. And then this d, I'll do this in a different color, du dx means I want to find a function that is in terms of u and x. So I have this u equals 3x plus 5. So if I find du dx, because this function right here is u is explicitly defined in terms of x, so I can find the derivative of u with respect to x by writing that notation, and then that is the derivative of this with respect to x is just 3. So then the entire derivative, dy dx is equal to dy du times du dx, and we just found these two things, so it is equal to dy du, which is right here, 2u, times du dx, which is right here, times 3, and that is 6u, but now we want to substitute back in what u is equal to, and that is 3x plus 5. I'm going to put that back in for this u right here. So 6 times 3x plus 5 is my final derivative. That is the derivative of this function. Okay, I'm going to do this exact same problem with a different approach. And we're going to do the approach that we used the other day by just looking at the derivative of the outside, multiply that by the derivative of the inside. So we have, this is how we wrote that definition. If y equals f of g of, oops, not f prime, f of g of x, then the derivative is the derivative of the outside, leaving the inside alone, and then you multiply that by the derivative of the inside, which now, so our inside here is, we're just going to ignore this for right now. Well, we can use that because that is our inside. Our inside is 3x plus 5, and our outside function is this 2. So finding the derivative of, the squaring is the outer function. So we're just going to pretend that this, we're just ignoring this. We're just going to use the power rule. You bring that 2 down, leave the inside alone, and the power rule says we subtract 1 from the exponent, so 2 minus 1 would be 1. So to the first power, which we don't need to write. And then you multiply, so that was doing the derivative of the outside, leaving that inside alone. And now we're going to multiply by the derivative of the inside here, which is just 3. And then you can take this 2 times that 3, and you get 6 times 3x plus 5. That is another way to find the derivative. That's the method I'm going to use. If you prefer the other method, go ahead and use it, or if you need me to do some more examples, come and find me and I will do that with you when I am back in class. All right, this one right here. Let's do cosine of t squared plus y. We're going to find y prime. So now if I was going to find the derivative of this with the other notation, I would want to write it like this, dy dt, because y is a function in terms of t. So this right here, you would say the derivative of y with respect to the variable t. Well, I'm not going to use that notation this time. I am going to take the derivative by finding the, determining what the outside function is. And this right here, the cosine function, is the outer function. So cosine of t squared plus 1, the inside is this t squared plus 1. So we take the derivative of the outside, so think about what that is. It's a negative sign. Do not do anything to the inside, and you're going to multiply that by the derivative of this inside. So ignore that cosine and ignore this negative sign for a second and just focus on this inside piece, multiply by the derivative of that, which is just 2t. And when you write that final answer, it's a negative 2t sine of t squared plus 1. You don't have to move the 2t in front, but it can be really helpful to do that just so you don't think that you're taking the sine of that 2t. Okay, why don't you guys look at this one, try to do it, pause the video, try to get this derivative, and then come back and I'll do it with you here. So, y prime, the derivative, so the outside is sine, so I'm going to take the derivative of sine, which is cosine, leave the inside as it is, now multiply, and multiplication, not addition, that's a big mistake I see a lot. We're going to multiply by the derivative of this inside, which is 2x plus 1. Again, I like to move that in the front just to keep track that I'm not actually taking the cosine of that piece. All right. So now we're going to find the slope of the tangent line to the curve of y equals sine to the 5th power of x. This right here, you have to remember, when you see this exponent, it means sine of x to the 5th. So the outer function is to the 5th power. So when I find the derivative, which is what we're doing when we're finding the slope of the tangent line to this curve, remember that that is the derivative. So the outer piece, the outer function, is raising this inside sine of x to the 5th power. So you bring the 5 in the front, leave the inside alone, and this needs to go in parentheses if you're going to write it after the sine of x, but you can also write it like this. Either way. I'm not done here though, because now I need to multiply by the derivative of the inside, which is sine of x. Its derivative is cosine of x. So you'll probably see it written like this rather than sine of x in that quantity to the 4th. So if the 4, the exponent, is in between the sign and the argument of the sign, then that means that the whole thing is to that power. And then we're finding the slope of the tangent line to the curve at a particular point where x equals pi over 3. So evaluating this derivative at pi over 3, it's 5. And this time I'm going to write sine of pi over 3 and raise that to the 4th like that, times cosine of pi over 3. If this was a show your work kind of problem, you really could stop at this point because you're done with the calculus, but now it's bringing back that trig, so we're going to do this. So I have 5 sine of pi over 3. If this is a 30, 60, 90 triangle, which is 30 degrees, remember, is pi over 6 radians, 60 is pi over 3. What is the sine? The ratio of the sides would look like this. What is the sine of pi over 3? Well, it's the opposite over the hypotenuse, so it's the square root of 3 over 2, and raise that to the 4th power. And then we're going to multiply that by cosine of pi over 3, which is cosine of pi over 3 is adjacent over hypotenuse, so that is 1/2. And then you could simplify. If you raise the square root of 3 to the 4th power, that means, well, you could do the square root of 3 squared and then raise that to the 4th, or to the 2nd power, and then over 2 to the 4th, which is 16. I'm going to put this 5 over 1, and then I have times 1/2. So the square root of 3 squared, that is just equal to 3, and so then when we square that 3, we get 9. So 5 times 9 on the top times 1 over 16 times 2, which is 32. So final answer is 45 over 32. And okay, I'm going to do one more problem. I'm going to do this. I'm almost out of time for this video, so I'm going to stop the video. You guys do this and then come back and check the work. All right, so you guys, hopefully you got this. This is my final answer here. 4x over 3 times the cubed root of x squared minus 1. Let me briefly go through this. First thing you want to do is rewrite a radical as an exponent. So the cubed root is the same thing as writing that thing to the 1/3 power. And then I multiplied my exponents together, so I ended up rewriting it to this. So this is f of x squared minus 1 to the 2/3 power. So the outside is the 2/3 power, the inside is x squared minus 1. Drop the 2/3 in the front and subtract 1 from that, so that's a negative 1/3, leaving that inside alone. And then multiply by the derivative of the inside, which is 2x. And then I multiplied you can multiply this 2x times that 2/3. If you put 2x over 1, you get 4x on the top over 3 times 1, which is 3. And then I wanted to get rid of my negative exponent, so I dropped it to the denominator. And remember that the 1/3 power can also be written as the cubed root. So that's that. And then I'm going to skip this for now. This is the assignment that I want you guys to be working on in 2-4. And you can skip any problems. There's only 2 of them, 47 and 55, that involve tangent. And I think one of them is cosecant, and we haven't done that yet. So 3 through 23, every other odd. 43 through 63, every other odd. 68, 75, 79, and 1 away. All right, I will see you on Wednesday. If you guys are really struggling, you can FaceTime me, or I can Zoom in with you. Tommy, you can just give me a call.